Okay, prove the irrationality. So in this video, we are going to prove that the nth root of 2 is an irrational number for every n greater than equals to 2, and we are going to do this using the fermat's last theorem. There are definitely other easy ways as well, right? Like using the proof by contradiction, like also one of them, and then we will go on to this proof using the fermat's last theorem. So let's say if you want to prove that cube root of 2 is irrational. So first of all, you can assume that it's rational number, and then you get to a contradiction, so which makes you believe that your assumption was wrong. So that's how we prove that it's irrational. So that's our flow of the proof. So first of all, let's assume that this is a rational number, and this can be written as in the form of p by q, where p and q are positive integers. They have to be positive, right? Because 2 is positive, any root of 2 would be positive, where p and q are positive integers. And also we can definitely assume that like p q are co-primes. That means it's in the reduced form, right? Because any fraction can basically be taken into a reduced form, right? So we are assuming that. So now after we assume that it can be written in this form, I can just cube both sides and say that 2 will be equal to p cube by q cube, and then p cube will just be 2 times q cube, right? Now since we see that there's a factor of 2 in the p cube, p should be even, right? So this implies that p should be even. P should be even. So that means p can be written as 2 times t. Again, that's if that's the case, I can substitute p, right? And this gives me, sorry, so then this gives me 8 times t cube as 2 times q cube, right? Again, if I cancel 2 from both sides, I get q cube as 4 times t cube. Again, since I see that like there's a factor of 2 on this side, because 4 has factor 2, again q should be even number, right? So that means again q can be written as let's say 2k. Now since we saw that like both p and q can be written as 2t and 2k, they definitely have a like common factor, like a common factor. Let me just write common factor 2, right? But earlier we assumed them to be co-prime. We assumed that they don't have any common factor. So that's how this proof works. Now since we have shown that our assumption was wrong, so that means we cannot assume cube root of 2 as a fraction of p over q, where p and q are integers and they are co-primes. So if there's no such fractions, this proves that cube root of 2 is irrational. This is a popular proof, but now we are going to prove it in a different way, and we are going to prove this for like any power n, right? But the power should be greater than 2. For 2 you can prove in the same way. For like power being 2 you can prove in the same way, right? For power being 1 you cannot prove because because the first root of 2 is not irrational, it's just 2, right? Okay, and for greater than equals to 3 you can use this way. So let's see how we do this. In this way also, first of all, we assume that we can write it as fraction p by q, where p and q are positive integers. Yeah, where p and q are positive integers, because that's the definition of rational numbers, right? P and q are positive integers. Okay, now we have assumed that this is rational number, and we have used the definition of rational number. Now definitely q should not be equals to 0. Definitely don't miss that point, because yeah, in the definition, if q is 0, that it doesn't make sense, right? So okay, now we have assumed it to be rational number. So if it's a rational number, I can say that this has a fraction p by q, where p and q are integers. And definitely, yeah, we can also assume that p and q are in like lowest terms. Yeah, but we don't need that for this proof, so yeah, let's not do it. So now I can take q to other side, so this becomes q times nth root of 2 is equals to p. If we raise both sides to power n, I can write it as q to the power n times 2 is equals to p to the power n. I can write it as p to the power n is equals to q to the power n plus q to the power n. So we get this expression. Now we'll use the Fermat's last theorem, which says that if I have an expression a to the power n plus b to the power n is equals to c to the power n, and n is greater than 2, right? I mean, n is an integer, n is an integer, please know that n is an integer, positive integer greater than 2, then Fermat's last theorem says that there's no solution for positive integers a, b, c. I mean, for there are no positive integers a, b, and c which satisfy this equation for any n greater than 2, right? So now we see that, like, this equation over here is in the same form, like a to the power n is equals to b to the power n plus c to the power n. And for this to satisfy, we need some integers p and q, right, to satisfy this equation. If this is true, there are such integers p and q which satisfy this equation. So that means the Fermat's theorem would be false if there are such p and q, right? And if Fermat's theorem were to be true, like, if there should not be any such p and q which are exactly satisfy this equation, like if let's say this satisfies the equation, then we get a solution p comma q comma q. But Fermat's theorem says that there's no solution. So due to which, since there's no such solution, so this equation in itself is a contradiction. So yeah, since we got to contradiction, our assumption is false, should be false, right? Because only false assumption lead to a false result. And yeah, if you haven't made mistakes in between, right? Okay, so that's why the assumption is false. So there are no such integers p and q whose fraction give us the nth root of 2, and therefore if there are no such integers p and q that make the fraction, that means it's not a rational number. So that's why nth root of 2 is not a rational number, and this proves the statement, right? So this was it. And yeah, definitely, since there are easier proofs, this is definitely overkill. But yeah, I do hope you saw a good application of Fermat's last theorem. That's it, and I look forward to seeing you in the upcoming videos too.